Hello, everyone. My name is Zhiqiang He. I am a first-year PhD student at University of Science and Technology of China. My talk today is about a new RDMA network virtualization solution suitable for VPC. This is joint work with researchers at Huawei and Professor Zhili Zhang from University of Minnesota. In public cloud, the VPC is the de facto way to provide a virtual network for virtual machines. Nowadays, the VPC demands for higher performance network because more and more network performance sensitive applications are deployed in the VPC, such as large-scale big data systems, key value store, and HPC applications. At the same time, RDMA is currently an important technology for building high-performance networking in data center. For now, the state-of-the-art RDMA can provide about 200 gigabits per second throughput and 2 microsecond round-trip latency under one switch. So bringing RDMA into VPC is a worthy work. VPC use network virtualization to provide a virtual network for each user. To understand how it works, we use the TCP/IP network as an example to show the basic vision. Suppose we launch 4 virtual machines on 2 host servers, and we join them into a virtual network and assign them with any IP addresses to allow the virtual machines for communicating with each other. VPC introduced a virtual switch on each host server to route the packets in the virtual network. Let us use an example to show how it works. Suppose virtual machine A wants to send some data to virtual machine D. It just writes both the data and the virtual machine D's IP address to a network packet. Then the packet will be injected into the virtual switch on the host. However, for now, the packet cannot be routed on the host network because the host network cannot understand the virtual IP address. So the virtual switch will encapsulate the packet with the host destination IP address. Then the packet can be successfully delivered to the destination host. And the destination host server simply trims off the actual host header and delivers this packet to the virtual machine D. However, the packet-based virtualization cannot be directly applied to the RDMA network. Let us show the problem by comparing the packet processing process between the TCP/IP network and the RDMA network. In virtualized environment, before injected into the network, packets will go through the virtual machine, the host server, and the NIC. Typically, both the VM and the host are software-based, and the NIC is hardware. In typical IP network, the network stack is in guest OS. Data sent from the application were first handled by the network stack, and the packets were then injected into the host. So we can use a virtual switch on the host to perform packet-based network virtualization. Compared to traditional TCP/IP network, RDMA offloads the network stack to the hardware called RNIC. Data sent from the application are directly delivered to the RNIC. Then the network packets are encapsulated in the RNIC. We can see that RDMA bypasses the host software and thereby the virtual switch. So we cannot directly use virtual switch to realize network virtualization for RDMA. So where and how to realize network virtualization and other features required by the VPC. To find out where to realize network virtualization, let's first take a look at the RDMA communication workflow in detail. Suppose the client application on the left virtual machine wants to send some data to the server application on the right virtual machine. Both of them should go through 3 stages. First, they should set up QP with peers IP address, where a QP is the same concept as socket endpoint in the TCP/IP network. With the QP, client and server can then call the send and receive separately to perform data transmission. Once finishing the data transmission, the application enters the cleanup stage to destroy the QP and other resources. For more details, let us zoom out the left side and push the other side onto the right corner. And we involve RDMA driver on the host and RDMA stack on the RNIC to show what just happened in each stage in detail. The QP setup stage will create a context called QPC in the RDMA driver and write the peer application's IP address into it. Then the QPC will be cached on the RNIC and used by the RDMA stack for packet processing. Once the QP is created and the QPC is configured, the application now can send data. The data sent from the application will directly DMA to the RNIC. Then the RDMA stack on the RNIC will encapsulate the data with the destination IP address configured in the QPC. Last, the packets will be injected in the network. As we can see, QPC is the key for RDMA stack for encapsulate the network packets. So the basic idea is that we can virtualize RDMA network by controlling the QPCs. For example, we can replace the virtual IP address to the host IP address for network virtualization. And since all the QPCs are maintained on the RDMA driver, we can perform QPC controlling in pure software. Following the basic idea, we propose MasQ for RDMA network virtualization. Now we give a C at MasQ's architecture. To control all the QPCs, MasQ introduces software on the host. Then any requests potentially manipulating the QPCs will first be forwarded to the MasQ software, and then the MasQ software delivers them to the RNIC for further processing if needed. For requests only referring the QPCs for data transmission, MasQ just leave them untouched. These requests still bypass host software and will be directly delivered to the RNIC. With this architecture, MasQ can provide two good features. First, with the MasQ software, it has the capability and the flexibility to realize network features required by the VPC. Second, since any data transmission bypasses the host software, the performance of the RDMA communication still remains. So, however, to build a well-functional RDMA for VPC based on the architecture, we can have three challenges to solve. First is how to provide a standard Rocky device in a virtual machine. This is important for supporting the applications who access the RDMA device using an IP address. Second and third is how to realize network virtualization and the application of security rules in MasQ software. In the following, I will introduce MasQ's three key mechanisms to solve these three challenges. And the design details can refer to our paper. First is how does MasQ provide a Rocky device in a virtual machine? A standard Rocky device consists of two interfaces, including an Ethernet interface and an RDMA interface. For best capability, the two interfaces should be both appeared in the virtual machine. To this end, MasQ uses the generic Ethernet interface virtualization method to provide the Ethernet interface and uses the hybrid I/O virtualization method to provide the virtual RDMA interface. The problem is that the two devices are separated. So VBound is proposed to bind the two devices to provide an Rocky device so that the application can access the RDMA interface using an IP address. We now give a C at MasQ's design on network virtualization. The core idea of network virtualization is to replace the virtual IP address in the QPC to the host IP address. To show how it works, let us first add an IP address for each host server where the virtual machine lives. And in the QP setup stage, the MasQ software replaces the virtual destination IP address with the host destination IP address and then writes it into the QPC. After the QPC is cached, data sent from the application will be encapsulated with the host IP by the RDMA stack. Then the packets will be injected into the host network and will be routed to the target virtual machine. To this point, network virtualization is achieved. We now give a C at MasQ's mechanism to prevent any bad guys from injecting traffic into the network. First, for each QP setup request, MasQ software will check the request whether they are allowed by the security rules. If a request is illegal, the MasQ software will reject it. What if a security rules is updated to mark the QP is illegal during data transmission? For this condition, MasQ software explodes the QP state in the QPC to shut down the QP by changing the state of the QP to error. Any subsequent data sent from the application will be dropped by the ONIC. We believe that by combining the two-level checks, bad guys won't have a chance to inject their traffic into the network. Now for the evaluation. In this part, we want to show that whether MasQ can provide competitive performance. We compare our solutions with three other RDMA networking. Host RDMA and SRIOV are involved as the baseline. FreeFlow is the state-of-the-art software-based solution for RDMA network virtualization. All candidates are evaluated in the same test bed consisting of two servers directly connected by 40 gigabits per second Rocky NICs. Each server is equipped with two powerful Intel CPUs and a big enough memory. And we run virtual machines using Camel and also run containers for FreeFlow using Docker because FreeFlow's prototype can only support containers. We first use perf test to measure the average latency for sending or writing a 2-byte message. The results show that MasQ can achieve the same latency as SRIOV. MasQ's latency is a little worse than host RDMA because MasQ's default mode will use the RNIC virtual function to enforce queues. We find that the RDMA performance over virtual function is worse than that over the physical function. So if queues is not needed, MasQ can directly map the QPs to the RNIC physical function. Our experiments show that MasQ can achieve almost the same latency as host RDMA by using the RNIC physical function. We also use perf test to measure the throughput with different message size. The result shows that the MasQ can achieve the same throughput as bare metal RDMA for all message size. For messages less than 8 kilobytes, MasQ performs better than FreeFlow. We also choose 3 types application benchmarks to test MasQ's performance. We included the Graph 500 benchmark for the HPC scenario and adapted RDMA-based HerdKV benchmark for the KV style, and Spark RDMA for the big data scenario. The experiment results showed that MasQ performs well in all different applications. And in the key value stone benchmark, MasQ achieved 10 times better throughput than FreeFlow. Finally, does MasQ introduce any overhead? MasQ takes slightly longer time in the QP setup stage. In our test case, the overhead is about 9% longer compared to SRIOV. And for most applications, QP setup is not on the critical section of the application overall performance, so the overhead can be negligible. We conclude by summarizing the contributions of this work. MasQ first proposed to virtualize RDMA network in QP setup phase, and then further proposed 3 practical mechanisms to realize features required by the VPC, including Rocky device abstraction, network virtualization, and applying security rules. A prototype of MasQ is implemented and evaluated against big data and HPC applications. The experiment results show that MasQ can be deployed in virtualized environment with negligible overhead. Here are some future work worth to explore. First, containers are also widely used in public clouds, so we can use MasQ's method to bring RDMA into containers. Second, virtual machine live migration is a very important feature in VPC. So enable live migration for RDMA capable virtual machine is also a worth future work. Thank you for your listening. Questions are welcome.